So let us go ahead and proceed further with the solution of the remaining questions are in practice question set. So the next question is question number 24. Write a solution using semaphores for the producer consumer problem. Explain the purpose of each semaphore used. So here is a clean semaphore based solution to the producer consumer problem along with an explanation of each semaphore's role. So the problem setup is we have a bounded buffer. So we are having a buffer whose size is capital N. So multiple producers will generate items or produce items. As the term signifies, producer means they will produce some items. And after producing those items, they will place those items within the buffer, right? And consumer's role is the vice versa. That is, they will consume those items produced by the producer, or consumer will remove the item from the buffer, right? So in this case, we will be using three semaphores. One is called empty semaphore, second full semaphore, and third one is called mutex semaphore. Empty semaphore will count the number of empty slots in the buffer. Uh, how many slots are empty in the buffer, which can be filled by the producer, which can where the producer can add the item, producer can produce the item, right? So the empty semaphore is first of all initialized to capital N, that is the size of the buffer, right? That is the size of the buffer is capital N, and the empty semaphore is also initialized to capital N. So the empty semaphore will ensure that producers don't overfill the buffer. Overfill means if the size of the buffer is n, uh, the producer cannot produce or place more than n items into the buffer, right? Second semaphore is the full semaphore that will count the number of filled slots in the buffer. That is how many slots are full in the buffer. So it is initialized to zero. It means that none of the slots are full. That is, none of the items have been produced by the producer and placed in the buffer. So full semaphore will also ensure customers don't try to consume from an empty buffer. So if the buffer is empty, if the buffer is empty, consumer cannot consume any item because there is no item in the buffer, right? And the third semaphore is the mutex semaphore. This is a binary semaphore, or you can say this is a log to ensure the mutual exclusion. So if you want mutual exclusion, we need to use this semaphore when accessing the buffer. And since this is a binary semaphore, mutex is a binary semaphore, the value can be 0 or 1, but the initial value of mutex is set to 1. So it will prevent race condition when multiple producers, consumers access the buffer simultaneously. This is the pseudocode solution to the producer consumer problem. So the producer will produce an item. This statement, item is being produced by the producer, right? Item is being produced by the producer. Now there are two types of operation. One is known as wait, another is known as signal. So wait empty means wait for an empty slot. Producer will wait if some slot become empty, right? Wait mutex means log buffer access. That is the mutex, as I have told you, it ensures mutual exclusion. So the log buffer is not being accessed, cannot be accessed by anyone because the buffer access is log now, right? After that, the producer will add an item to the buffer, right? Producer will add an item to the buffer using the insert, right? Signal mutex means now the buffer is unlocked, right? And signal full means now the count of filled slots is incremented by one. Why? Because the producer has produced an item, inserted an item, and one buffer is and placed that item into the buffer. That's why signal full indicates the count of filled slots is incremented, right? So do while condition. This is the producer code. Similarly, vice versa is the consumer code. Wait full means uh, consumer has to wait for a filled slot by executing this wait full. Wait full means consumer has to wait for a filled slot until and unless a slot has been filled. Only that consumer can consume. So wait full means consumer has to wait for a filled slot. And again, this wait mutex means the buffer is now logged. No one can access the buffer. Now the item will be removed or consumed by the consumer, and signal mutex means now the buffer can be accessed. The buffer is unlocked. Signal empty means consumer has now consumed an item, and now one slot will be empty because one slot has been consumed by the consumer. So signal empty means count of empty slots is incremented, right? And then the item will be consumed by the consumer, right? So this is the very popular solution to the producer-consumer problem with the help of the semaphore. The purpose of each semaphore has already been told to you. Once again, empty semaphore prevents producer from inserting when the buffer is full. Full semaphore prevents consumer from removing when the buffer is empty. And the mutex semaphore ensures only one thread, either producer or consumer, modifies the buffer at a time. That is only one. Uh, Either the producer can produce or consumer can consume. Both cannot do simultaneously and avoiding the data corruption. So this design guarantees no buffer overflow, no buffer underflow. So there is no buffer overflow. We are thankful to the empty semaphore. There is no buffer underflow. We are thankful to the full semaphore and safe concurrent access. We are thankful to the mutex semaphore, right? Now the question number 25. Consider the following locking method, that is while test and set lock, critical section lock is equal to false. Analyze how it behaves with multiple processes and mention one drawback, right? So see, this locking method is based on busy waiting or also known as spin lock using the test and set instruction. Behavior with multiple processes. When several processes attempt to enter the critical section, each executes while test and set lock. The test and set instruction atomically sets lock to true and returns its old value. If the old value was false, the process enters the critical section. If the old value was true, because the old value was true, now the value will become true. The process will enter the critical section. If the old value was true, it will become false, and process keeps spinning in the loop until the lock becomes available. So the once a process finishes its critical section, it releases the lock by setting lock equal to false. So lock equal to false means that process has already finished its execution in its critical section. So at that point, the lock was true. Once the process has finished its execution in its critical section, the lock value can be set now to false, right? So I hope you have understood the value of lock. What does we mean? What do you mean? What do we mean by setting the value of false or true to the lock variable, right? Lock, right? At that point, one of the waiting processes will succeed in acquiring the lock and enter the critical section. The drawback, the main drawback is the busy waiting or the wasted CPU cycles. That is, while waiting, processes continuously execute the test and set loop, consuming processor time without doing useful work. This can lead to performance degradation, especially if many processes are contending for the loop. Contending means competing for the loop. If every many processes are in the need of acquiring the loop, right? So in multiprocessor systems, it also causes cache invalidations and bus traffic, further reducing reducing the efficiency. So in short, the method ensures mutual exclusion but suffers from inefficiency due to busy waiting. Next question is question number 26. Explain how priority scheduling works. What is starvation? How can it be prevented? So, priority scheduling. Each process is assigned a priority number. CPU is allocated to the process with highest priority. We have already solved such CPU scheduling algorithm in the previous questions. So, there are two types of priority scheduling: preemptive and non-preemptive. Preemptive means running process is preempted if some higher priority arrives. So lower priority running process will be preempted and CPU will be given to higher priority process. So that is preemptive priority scheduling. Then is the non other is the other variation of the priority scheduling is non-preemptive, where the running processes first complete their entire CPU burst time, right? Priority assignment. So convention, mostly used convention is that is lower number is considered as a higher priority, but it may vary, right? It can be internal, that is time limit or memory requirement can be there. It can be external also based on importance and payment. So what is starvation? Starvation occurs when a process waits indefinitely because other processes with higher priority keep arriving, right? Example is low priority process never gets CPU because high priority processes continuously arrive. Now, how we can prevent it? First method to prevent is the aging, that is gradually increasing the priority of waiting processes. Those processes which are waiting for a long time, we can increase the priority of those processes, right? Eventually, even low priority process becomes higher priority. implementation priority equal to base priority minus waiting time divided by k. So we can increase the priority by using this formula. Second, by using the multi-level feedback queue. So processes move between queues based on the behavior. Long waiting processes promoted to higher queues. So this is the second method by which we can remove the starvation. Third is by priority ceiling, that is by setting the maximum and minimum priority limits. It prevents extreme priority differences. Fourth is time limit, that is set maximum waiting time. That is a process can wait for a such a we set some time and process can wait for that time. If the time exceeds, then the CPU should be allocated to that process. So starvation will can be removed by using this. For scheduling after timeout, as I have said, after timeout, we have to schedule that process. CPU should be given to that process for execution. Best solution out of these four is the aging, that is simply increasing the priority, maintain the priority concept while ensuring the fairness. Next question is given we are having given three processes P1, P2, P3. Right. We have already solved such type of problems. Arrival time and bus time have been given to us. Now each process has CPU and IO pattern. What is the pattern? That is 20% CPU, 30% IO, then 50% CPU. We have to apply first come first served CPU scheduling algorithm, calculate the waiting time, turnaround time, and response time. And also we have to compute the analyze the CPU utilization. So let us carefully break down this step by step. So the arrival time and bus time given has been given to us, and the pattern is 20% CPU, 30% IO, 50% CPU. Right. So we can take this P1. P1 P1 burst time is 18. So we have to divide 18 into 20%, 30, and 15%. So CPU first CPU burst 3.6 IO. How 3.6 has come? That is 20 divided by 100 into 18. Then 30 IO 5.4. How does this value come? 30 divided by 100 into 18. Similarly, CPU 2 is equal to 9 means 50 divided by 100 into 18. Similarly, we can compute the remaining value. Now we have to compute the scheduling order, or we can also draw the Gantt chart. So we schedule strictly in arrival order, because first come first serve says that the processes should be allocated CPU burst time in the order of their arrival. So P1 arrive first, then P2 arrive, then P3. So this is the first come first served. So P1 starts at 0 because the arrival time of P1 is 0, right? So it runs for how much CPU? First CPU 3.6. Then it goes to IO for next 5.4, right? And then during P1's IO, during this P1's IO, the CPU is free, right? CPU is free because P1 is doing IO, so CPU is free, right? So at time arrival time of P2 is 2. So P2 arrives at time 2 and it runs for 4.8, right? It runs for 4.8. Then it goes for IO for 7.2, right? While P2 is in IO, now P3 arrival time is 4. So P3 arrives at time 4 and run its CPU 2.4, right? Then it goes for IO for at 3.6, right? So after each process completes IO, they return for CPU2. Now CPU2 time will be for P1, P2, P3 will be executed, right? In first come first served order. So we can easily compute the completion time. So 0 to 3.6 P1, then 3.6 to 9 IO, right? Then 9 to remaining time is because bus time of P1 is 18, remaining time will be 9 to 18. So the completion time will be 18. Similarly, completion time for P2 will be 30, completion time for P3 will be 36, right? So we can easily compute these all these times. We have already become aware about how to compute these times. So we can apply those formulas and compute the corresponding values of turnaround time, waiting, and response time, right? CPU utilization, total elapsed time is how much? P3 completes its execution at 36 units of time. And sum of all CPU bursts. You can see here sum of all CPU bursts. That is sum of all CPU bursts. 3.6 plus 9 plus 4.8 plus 12 2.4 plus 6. This is comes out to be again 36. Sorry, 37.8. So actual CPU busy time can be is 36, right? So the again the CPU utilization will be 36 divided by 36 into 100, that is 100%. Right. So final results are these, that is turnaround time, waiting time, run time. We can compute easily, right? Now the next problem is problem number 32. That is given again three processes P1, P2, P3. Arrival time, bus time has been given to us. Again 30% CPU, 40% IO, 30% CPU. So we have to apply the non-preemptive. SJF is the non-preemptive version. Shortest job first. Compute performance metric and suitability we have to determine, right? So again we can see here. So 30% CPU means P1 burst time is 18. So 30 divided by 18 into, sorry, 30 divided by 100 into 18, that is 5.4. We take the round of values, that is 5. Similarly here will be 5. Similarly we can compute this IO. How this IO? Burst time of P1 is 18. So 40 divided by 100 into 18, IO will be time will be 7.2. So we can, it is similar to the previous problem, but the scheduling algorithm has been changed now. So initial CPU burst at time t, at time 0, the P1 arrives, right? Arrival time of P1 is 0. So P1 arrives at time 0. P1, only P1 is available at time 0. P1 is available, so it runs for 5 minutes. It will complete its complete 5 CPU burst, this 5, right? Because it is a non-preemptive version. Then at T1, at time arrival time of P2 is 1. So at time 1, P2 arrives, and P2 burst is also 5, this 5. So it will run for 5. Then at T at time 2, arrival time of P3 is 2, burst time is 10. So burst time is 10. Burst time for P3 is 10. Okay. But burst time for P3 is 10. This burst time of P3 is 10, right? So we divide 30 divided by 100 into 10, 3. 40 divided by 100 into 10, 4. 30 divided by 100 into 10, 3. So now P3 will execute for 3 units of burst time, right? So shortest job first says that because see at time t0 P1 arrives and it will run for 5 units of time, this 5 unit time. Okay, then CPU burst time for at time 1 after P1's first CPU burst. So up to 5 P1 has executed for 5 units of burst time. So after 5 units of time, okay. So at the time T P2 and P3 both arrives up to 5 units of time. P2 and P3 both arrive because arrival time of P2 is 1, P3 is 2. So both of them arrive because P1 has executed up to 5 units of burst of time. Up to 5 units of burst time, both of P2 and P3 arrives, but burst time of P2 is 15. Sorry, we have to say here. Burst time of P2 is 5 and P3 is 3. So it is shortest job first. So P3 has shortest burst time of 3 in comparison to burst time of 5 for P2. So P3 will be executed ahead of P2. So P2, so it will pick, SJF will pick P3 first because it is shortest burst time. As you can see here, the burst time of P3 is 3, P2 is 5. So shortest for burst time for is for P3. So P3 will execute first before P2, right? So execution order will be P1, P3, and P2. Clear? So second CPU burst will also be same because this is also same. This and this is same, right? This and this is same, right? This and this is same, right? So the same execution cycle will be for second CPU burst. For second step, Uh, okay, right. So timeline will be 0 to 5, right? That is P1. Then P3 from for 3 unit of burst of time. Then 8 to 13. That is P2 has burst time of 5. Then 13 to 16 CPU after IO finishes. So from after P2, uh, right. So after P2, the burst time which shortest out of these three is 5, 5, and 3. So P3, P1, P2. P3, P1, P2. So P3, P1, P2. So we can now compute the metrics, performance metrics, that is completion time, turnaround time, all the formulas are known to us, right? So suitability of shortest job first, that is the non-preemptive. Advantages are it minimizes the average waiting time. Short processes like P3 will finish quickly and it will result in responsiveness, good responsiveness. Drawbacks are, demerits are longer jobs, P2. Longer jobs which are having high burst time suffer starvation risk if many short jobs keep arriving. Requires precise knowledge of burst time, which is often impractical. With input-output bound processes, shorter jobs may cause inefficiency since CPU bursts are interleaved with input-output waits. So in this case, shorter job first gave low waiting times overall, but P2 had significantly higher waiting compared to P1 and P3. For mixed CPU IO workloads, round robin or multi-level feedback queue is usually more suitable, right? Next question is question number 33. So SRTF and round robin we have already discussed. You can solve this problem number 33 at your own because we have already solved such type of problem in the previous part, right? uh, Nonetheless, for the sake of completeness, I can show you this the slide of, sorry, solution of this problem. Clear? You can see the solution of this problem. This is the step-by-step execution. Using this step-by-step execution, you can easily draw the Gantt chart. Clear? So we have to apply two algorithms. Shortest remaining time first means preemptive. SJF was non-preemptive. Shortest remaining SRTF, shortest remaining time first is preemptive. Round robin. Clear? So you can apply first SRTF, then round robin. You can easily then draw the Gantt chart. After drawing the Gantt chart, you can compute these all the time completion, turnaround, waiting, response time. All these you can calculate, right? This is the step-by-step execution for round robin CPU scheduling algorithm. Using this step-by-step execution, you can easily draw the Gantt chart again. And after drawing the Gantt chart, again you can compute this performance metric, that is completion time, turnaround time, and waiting time. Right? We have already solved such type of problems. Method is same. Right? This is the completion order in SRTF and round robin. Right? In SRTF, this is the order, right? In RR, this is the order, right? Round robin, this is the order of execution. You can also draw the Gantt chart at your own, right? So numerical for performance is identical in each case. Behavior differs. SRTF, that is the preemptive shortest remaining time first CPU scheduling favors shorter jobs immediately, better for minimizing waiting of short tasks. Whereas round robin ensures fairness and time sharing, preventing starvation. So in this data set, both yield the same averages, but round robin gives more predictable fairness, while shortest remaining time first is more efficient in general for minimizing average waiting time. Right. Then the question number 34, we have to use the first come first served and shortest job first is the non-preemptive. Again, this we have solved such type of problems earlier. Then question number 35. In this case, we have to apply the priority scheduling. Priority scheduling we have already discussed, but in this case we have to apply two types of priority scheduling: preemptive and non-preemptive. Preemptive means if some higher priority process arrives, then the currently running process will be preempted, and the CPU will be allocated to that higher priority process. Non-preemptive means we have already discussed. That is, once the CPU has been allocated to some process based on the priority, then it will not be preempted. It will consume all the burst time at all, and it will be CPU will be allocated for entire burst time, right? So lower number means higher priority. As you can see here, P1 is having priority 2, PR is having priority, P2 is having priority 1, P3 is priority 3, and P4 is also priority 2. So lower number occurs in P2. So P2 is the process with the highest priority. So first of all, this process should be given preference, right? Or however, I can show you the steps here. Question number 34. Sorry. This is the solution to 34. I can show you. This is the solution to problem number 34, where we have to apply FCFS, first come first served, and shortest job first. You can see here we have computed turnaround time, waiting time, right? You can draw the Gantt chart also. This is the step-by-step scheduling for shortest job first for problem number 34. And based on this, we can draw the Gantt chart, right? This is step-by-step scheduling only helps in drawing the Gantt chart, right? So you can draw the Gantt chart. Now, question number 35, that is, we have to apply the preemptive and non-preemptive priority scheduling. So you can see first the non-preemptive priority scheduling. These are the step-by-step execution. You can draw the Gantt chart, right? In non-preemptive. So this is the non-preemptive priority scheduling. You can draw the Gantt chart. And for priority scheduling, this is the step-by-step execution. Based on this step-by-step execution in preemptive priority scheduling, we can draw the Gantt chart here also, right? This is the Gantt chart. So we are done with the problem number 35 as well. Now we come to 36. That is, we are having a variable x is equal to 0 is modified by 4 processes. That is, the value of x is modified by 4 processes. We are having 4 processes, namely w, x, y, z. Semaphore s is given to us, whose value is 1. We have to find the maximum possible value of x. And what happens if the value of semaphore s is equal to 1, right? So first of all, we have to compute the maximum possible value of x. And what happens if the value of semaphore s is 1, right? So the problem number 36 can be solved like this. Now, initial value of x is what? 0. Value of x is 0. Initial value of x is 0. 4 processes we are having w, x, y, z. Wx processes add 1 into x. Processes y and z subtract 2 from value of x, right? So semaphore s equal to 1, it means it is a binary semaphore. It is a binary semaphore. And binary semaphore is used for what? For ensuring the mutual exclusion. So first is where we are using no semaphore, without semaphore. That is, there is no synchronization. So if there is no synchronization, if there is no synchronization, it means all the 4 processes can interleave arbitrarily, randomly. So possible maximum value occurs if W and X execute first. W and X execute first. That is, W and X. That is, they add 1. So initial value is 0. 0 plus 1, 1. 1 plus 1, 2. So W and X are adding 1 into value of X. Initial value was 0. Then W adds 1 into X. And X also, this X. This X also add 1 to value, updated value of X. So the value of X will become 2, right? Then Y and Z subtract. That is, Y and Z subtract 2 from value of X. Value of X was 2, right here. 2 minus 2 minus 2. So minus 2. So final value is minus 2. But the maximum value can occur with 2. So the maximum possible value in this scenario is this 2. We were supposed to compute this value. Okay. Now the case 2. Case 2 where we apply the semaphore. And the value of semaphore is 1. So semaphore is used for what? For ensuring mutual exclusion. That is, only one process execute its critical section at a time. This means each operation completes fully before another begins, right? Each operation should complete before the another operation begin, right? Regardless of order, all the four processes will eventually execute. So net effect will be 0 plus 1 plus 1 minus 2 minus 2, right? So if semaphore with semaphore protection, final value is deterministically minus 2, right? So the maximum value possible value of x is 2, which we have computed without semaphore, and with semaphore s equal to 1, mutual exclusion enforces all operation to complete sequentially. So the final value is minus 2. So you can see all the operations have been performed sequentially, right? So the final value is minus 2, right? Now the next problem. Problem number 37. Two processes must execute alternately. That is, there are two processes P and Q. They are being executed alternately. Firstly, P execute, then Q, then P, then Q, then P, alternately. We have to design a semaphore-based solution and explain why it avoids deadlock, right? So problem number 37. So here is a clean semaphore-based design for enforcing strict alternation between two processes P and Q. So this is a semaphore based solution. We use two semaphore. The name of first semaphore is S underscore P. The name of second semaphore is S underscore Q. So the first semaphore SP is initialized to 1. What does it mean? It allows P to start first. Then SQ initialized to 0. What does it mean? It blocks Q until the P finishes, right? So the pseudocode is while true, wait SP means P. I have earlier told you these two operations, wait and signal. So wait means the process P will wait for its turn. Okay, okay. When it turns comes, P is in the critical section and execute its critical section completely. Then P execute its task here. Then signal SQ. Now P has finished its execution. Now Q can be allowed to run next. So signal operation means process Q is being allowed to run now, right? So this was the pseudocode for process P. Similarly for process Q, vice versa will be there. Earlier P was waiting for its turn. Now Q will be waiting for its turn. After waiting, Q will enter its critical section and it will get its critical section executed completely. Then signal SP. It will now allow P to run next, right? So this is the solution. Simple is that. This I have already explained. So this is the alternation. So this cycle repeats. First P execute, then Q, then P, then Q. Why the deadlock is avoided in this case? So at any time, exactly one process is allowed to proceed. So no, there is no deadlock. The other is blocked. The signaling ensures that once a process completes, it always unblocks the other. There is no circular wait or resource hold. So none of the conditions for the deadlock is fulfilling here. So that's why there is no deadlock. Hence, no deadlock occurs and alternation is guaranteed. Next problem number is 38. 38 problem number says system has four identical printers shared by many processes. Design a semaphore solution to control access. What happens if a semaphore value is set incorrectly? Right? We are having four printers shared by many processes. So we have to design a semaphore solution to control the access by the processes to four identical printers. So first of all, need to initialize the counting semaphore. The name of the counting semaphore is printer underscore sem. And the value is 4 because there are four identical printers available, right? So each process that wants to use a printer must wait. Wait means P operation on printer semaphore. And wait means decreasing. Signal means increasing. So you have to remember, whenever you are executing wait operation, it means you are decreasing the value of semaphore. Whenever you are executing the signal operation, it means you are increasing the value of semaphore, right? So wait operation is also known as P operation. Signal operation is also known as V operation, right? So wait operation will decrease the semaphore value by 1. If the value is already 0, the process is blocked until a printer becomes free. Because if the value of semaphore is 0, it means printer is not available. So process is blocked until the printer becomes free. When the printer becomes free, the printer can be accessed, right? And the accessing the printer means The process is in its critical section. After that, process has finished its execution. Process has used the printer. Then it increases the value semaphore by 1, making the printer available again. So this is the pseudocode that is wait. Wait printer. This printer Sam is the semaphore that is requesting a printer. So after requesting a printer, printer will be used. Once the printer has been used, then printer will be released using the signal operation. Right? What happens if semaphore value is set incorrectly? So if the value of the semaphore is too high, for example, we have initially set the value of semaphore to 4, but if we initialize to 5, then what happens? Then in that case, more processes than available printer. Number of available printers are 4 and number of processes are more than 4. So more processes than available printers may enter simultaneously. This causes over allocation. Multiple processes may try to use the same physical printer, leading to conflicts, corrupted output, or hardware contention or conflict. Right? If the value of semaphore is too low, for example, if the value of semaphore is set to 3 or less, fewer processes than available printer can access them at once. This causes underutilization. Some printers remain idle even though processes are waiting, right? If the value of the semaphore is negative or 0, in that case, no process can access a printer initially. System deadlock or starvation occurs until the semaphore is corrected. So these are the implications of setting the value of the semaphore incorrectly, right? I have told you 3 scenarios: when the value of the semaphore is set too high, when set to too low, when the value of semaphore is initialized to negative or 0, right? So the semaphore value must exactly match the number of reticle resources. So the value of the semaphore should be 4. That is equal to the number of printers. That is, number of printers are 4. So the value of semaphore should also be equal to 4, right? Now we are going to question number 39. 10 processes share a critical section using a mutex semaphore equal to 1. One process incorrectly uses signal before wait. Analyze the effect and correctness of the system, right? So let us break this down carefully. 10 processes share a critical section protected by a mutex initialized to 1. So this is a mutex semaphore, that is value is 1. Normally each process should use wait mutex and will enter its critical section, then signal mutex, but one process mistakenly executes signal before wait. So if the signal is executed before the wait, in that case it results in incorrect order. So what will be the effect of incorrect order? Semaphore misuse. Signal mutex incremented the semaphore value before entering the critical section. Since the mutex was initialized to 1, after the error, it will become 2. So second is loss of mutual exclusion. With mutex value of 2, two processes can simultaneously execute in the critical section. And this allows two processes to enter the critical section at the same time. So the mutual exclusion is violated. Cascade effect. If this faulty process repeats the mistake, the semaphore value may keep increasing. Eventually, multiple processes, more than one, can enter the critical section concurrently, leading to race condition, data corruption, or inconsistent state. Correctness is violated. The fundamental property of a mutex is broken. That is, ensuring only one process can enter into its critical section is violated. System is not safe because the critical section can be accessed by multiple processes simultaneously. The faulty process essentially convert the mutex into a counting semaphore, which is not the intended mechanism. Correction is we already have to execute wait before signal. Never execute signal before wait, right? So in summary, the incorrect ordering, that is, if we are executing signal before wait, destroys the mutual exclusion guarantee, right? Now we come to question number 40, that is, a system uses test and set logging with multiple processes arriving at the same time. Analyze how many processes can enter the critical section, possibility of starvation, and suggest the improvement, right? So let us break down this clearly. How test and set logging works. Test and set, that is abbreviated as TAS, is a hardware supported atomic instruction used to implement spin locks. A process repeatedly executes test and set on a lock variable until it acquires the lock. So acquiring the lock means it can enter in critical section. So once inside the critical section, the process after resets the lock to 0, right? So in order to enter the critical section, the process has to acquire the lock, right? How many processes can enter the critical section? Only one process can at a time can enter the critical section, because test and set ensures the atomicity. Even if multiple processes arrive simultaneously, only one of them succeeds. right? And others will keep spinning until it is released. So there is a possibility of starvation. Starvation is always possible, and test and set does not guarantee fairness. A process waiting for a long time may be repeatedly overtaken by other processes that arrive later but manage to grab the log first. So this is especially problematic under heavy contention as some processes may never get a chance to enter the critical section. So these are some of the improvement methods we can be that can be suggested to avoid the starvation and reduce the contention. So you can read out at your own. Clear? So with that being said, we conclude this practice based set.